The U.S. military released an RFI for a next-generation aerial target. The need for versatility in these aircraft has led to the desire for rocket-assisted takeoff capabilities. The aircraft must additionally be capable of supersonic dashes and high-speed maneuvering. This is Team 8's proposal for the next-generation aerial target. To start the design process, certain criteria were pulled from the RFI. This consisted of the gross takeoff weight, payload capacity, fuel capacity, and more. For the mission legs, Mach numbers, altitudes, and durations were given. A drag polar was also assumed to calculate values such as required thrust and fuel burned. The proposed NGAT design was created in the attempt to complete the mission profile, which can be seen here. To start the design process, a mission analysis was performed. This entailed finding important values for each leg, such as thrust-specific fuel consumption, minimum required thrust, and aircraft weight by using requested flight parameters and an assumed drag polar. A parametric cycle analysis was then used to compare different levels of technology for engines as well as engine design parameters and the figures of merit associated with them. By comparing carpet plots at different levels of technology, a level of technology of 4 was chosen, which incorporates modern-day technology. From this PCA and the carpet plot seen here, 3 Canada engines were chosen to move forward with. The design choices of Pi-C and TT4 for Canada engines 1, 2, and 3 from the PCA can be seen in the table here. EPA was used to look at how the Canada engines performed at different flight conditions and throttle settings, as well as to size the engines. The performance of each engine was taken into consideration when choosing the final design. Kinematics was used with the given requirements to find velocity at burnout, acceleration, altitude at burnout, and launch angle. The calculated values can be seen here. The chosen engine was determined by how the engine performed in EPA while considering any implications. Engine 2 was chosen based on a few parameters. It was smaller than Engine 1, which means less weight and easier integration into the airframe. The other factor driving the decision was thrust-specific fuel consumption. The decrease in TSFC from increasing the Pi-C from 8 to 9 in Engine 3 is negligible and was determined to not be worth the added complexity in manufacturing. The rocket chosen was based on open motor simulations. The final choice was a neutral thrust curve that had an average thrust of 1,310 pound-force over roughly 5.5 seconds with a total impulse of 7,200 pound-force seconds. When selecting an engine, the team had to weigh both cost and complexity against performance. It was decided to use a level of technology of 4 because the performance gain going to a level of technology of 5 was not enough to justify the cost and complexity of the engine. Trade-offs of TSFC and specific thrust also had to be considered. The trade-offs of specific thrust and TSFC with the compressor ratio helped thrust and fuel efficiency as the compressor ratio went higher and limited the engine at a ratio of 8 because the benefits were becoming minimal. The goal of the engine was to have a low TSFC without sacrificing much specific thrust. Using the specific thrust at each mission leg, mass flow rate was calculated. The maximum required was at the dash leg with an uncorrected mass flow rate of 33 pound-mass per second and corrected of 55.9. This corrected mass flow rate led to a required engine diameter of 14.7 inches. In the table below, one can see how much additive drag was created and the resulting installation losses in each leg. Throttle hooks and Mach sweeps are performed for each engine in EPA. The throttle hooks are performed at different altitudes as well as flight speeds. The Mach sweeps are performed as different flight speeds to see the effect of altitude on both thrust and thrust-specific fuel consumption. Changing some mission parameters with respect to altitude may need to be considered. For example, by flying at higher altitude in the cruise legs, the thrust-specific fuel consumption of the engine is decreased while the required thrust is still met. The solid rocket motor design was created using requirements based on inertia, weight, drag, and kinematics discussed previously. Open motor was used to estimate the specifics of the motor design. The final design delivers a total impulse of approximately 7,200 pound-force seconds in 5.5 seconds using 3 10-inch base cranes. The fully assembled weight of the motor is approximately 75 pounds, consisting of 42 pounds of propellant. A roughly neutral thrust curve was desired to produce a more uniform thrust throughout the burn. The two rocket motors together produce over 14,400 pound-force seconds of total impulse to accelerate the vehicle in excess of 150 miles per hour, exceeding the design requirement by approximately 14%. The rocket was mounted to the aircraft using T-slot linear bearings. This allows the rocket to fall away upon burnout. There will be a thrust plate in front of the forward lug on the plane that will transfer the thrust into the wing box. The aircraft and launch rail integration can be seen here, as well as the rocket being installed on the aircraft. In order to account for unforeseen mission payload and loading conditions, a variable position rocket mounting system was employed. This allows for vertical rocket position variation to best suit the particular mission. An FEA analysis was conducted on the radar bracket to ensure sound material choice and structural design. As can be seen, the deformation and stresses were well within the capabilities of the aircraft grade 2024 aluminum alloy. Regarding radar stability, the rockets will be placed on the approximate vertical CG location using the variable position mounting system, ensuring that the thrust line acts through the CG to avoid adverse pitching moments. Additionally, the recovery will be enabled by an 8-foot parachute and mechanical sliding release mechanism. Concerning longitudinal changes in CG position as the rocket motor burns and subsequently releases from the aircraft, the shift in CG is well within acceptable limits, moving less than an inch in both full and empty payload configurations. The radar launch rail is made of 4-inch square tubing that is a 1/4 inch thick. It is set up at a 20-degree launch angle with 2 cradles to hold the rocket and slide into the T-slot channel. There's a stop at the end of the rail to keep the cradles from sliding off the end of the rail at takeoff. A shear pin is used to ensure both rockets fire before takeoff. The launch sequence will begin with the vehicle stationary and the launch rail supported by 2 cradles, then we'll proceed to take off and detach the rocket engines for recovery. Thank you for watching. This has been Team A's design presentation for a next generation aerial target with radar capabilities.